Alright, you good. Wow.
Alright, good. Yeah, these are all washed.
Good enough.
I see that it's at 800 to 200.
Yes.
He needs to put it in.
Is it 0.74? Yeah.
That's what I said.
It's 7.45.
I'll speed it up, bro.
But less than 5. Oh, okay. How do I hold it?
No, start. So 6. 6:30. 6:33. So you don't have to take it back out. You just go to simple reads. Oh yeah. Oh no, he didn't. Yeah. Word. Yeah. Right. 0. Okay.
Should we still throw it real quick?
It's fine. Oh.
Take a moment.
Okay. And then take it out and clean up the station. There we go.
Alright, so the Baer-Lambert law is a fundamental relationship in analytical chemistry, particularly in the UV visible spectroscopy, which states that the concentration of a chemical substance in a solution is directly proportional to the amount of light absorbed by that solution.
The equation involves 4 variables, each with a specific meaning. A is absorbance, epsilon is molar absorptivity, B is path length, and C is concentration.
And then the equation itself is A equals epsilon times B times C. So the relationship between absorbance and concentration, there's a direct proportionality. The Baer-Lambert law establishes a linear direct relationship between A and C, provided the path length and molar absorptivity are constant. So this means that doubling the concentration will result in doubling the absorbance. This linear relationship will allow scientists to create a standard curve using known standards, which is then used to determine the concentration of an unknown sample.
Effective filling shows the blank, then fill the the blank significantly effective measures the purpose of the blank accounts for any light for like solvent, which is temperature or any purity of the solvent, and the effect of chemical when the spectrophotometer is not there or like the instrument measures the total product of the sample, which is total of the sample of the absorbance of the event. Max is fully defined as the wavelength at which the substance given its maximum light absorption.
The data from the full spectrum scan shows the absorbance value for every tested wavelength. Our goal is to identify the peak on this plot, the specific point where the absorbance value is the highest.
To confirm purity and identity of contaminants, a full spectrum acts as a chemical fingerprint for a compound. If an unexpected peak appears at a different wavelength, it suggests that the sample is contaminated with another substance. For example, if you expect a protein to absorb around 280 nanometers but also see a strong peak at 260 nanometers, it might indicate contamination by nucleic acids.
Alright, to optimize sensitivity and specificity, different chemical compounds absorb light most strongly at different wavelengths. Scanning allows you to determine the best possible wavelength to use for your analysis. Using the wavelength where the compound absorbs most strongly maximizes the signal and minimizes interference from other compounds that may not absorb well at that specific wavelength.